When we did the penny sampling activity, I wanted you to notice a few things in particular. First of all, here's the date. Here are all the dates of the pennies in the entire bag. So this is the distribution of the population of penny years. Down below is an example of a distribution of a sample of penny dates. In this particular case, I think there were 99 pennies sampled from the bag. Notice the mean and standard deviation are very similar here from the population and the sample. So as the sample size increases, what you should notice about the distribution of the sample of individual penny dates is that it begins to look more and more like the population distribution. Kind of an obvious result, but something that students tend to mix up once we start talking about the sampling distribution. Now let's take a look at what happens when we take samples of different sizes from the original population. What we did here was take samples of size 5 from the original population, find the mean of the sample, and plot the mean. And we did this for 1,000 samples. We did this for a sample of size 5, a sample of size 20, and a sample of size 30. Notice that the mean for each of these is about the same, and it's equivalent to the population mean. So here's one of the characteristics that we noticed. We noticed that the sampling distribution, actually I won't rewrite that, the sampling distribution of sample means has these characteristics. The center is the same as the center of the population. In words, we say that that is the mean of the sample means equals the population mean. In symbols, we would say mu of x bar equals mu. Another thing that's very obvious is as the sample size increases, the distribution of the sample means decreases, or the spread, the amount of variability in the distribution of sample means decreases. So when we think of spread or variability, as n increases, the distribution of x bar decreases. And as a matter of fact, we did some computations and found out that sigma of x bar actually equals sigma divided by the square root of n. Now these two particular characteristics are true no matter what the original population looks like, as long as the trials are independent. So the condition here would be independent trials. And remember, if the trials are not independent, we can assume they are reasonably independent if n is less than 1/10 of big N. In other words, the sample size is less than 1/10 of the population size. Now, one other obvious thing you notice is that the original population is very skewed to the left, but the distribution of sample means is fairly normal looking. It's maybe slightly skewed to the left, but not much. So we can see that the shape is approximately normal. Now that is not necessarily true for every single population unless a certain condition is met. So what condition do we need for sample means? For sample proportion, we used NP and NQ greater than or equal to 10 to tell us that the distribution of sample proportions was approximately normal. But what about the sampling distribution of sample means? Well, we're going to take a look at distribution of sample means using this app on StatCrunch. So we're going to start with a bell-shaped distribution. In other words, a distribution that's normal. And I'm going to take a sample size of a small sample size of 5. and I'm going to draw a sample. So this represents the 5 individuals in the sample, and then this would be the sample mean. And I'll do this a few times. So you can see the sample, the distribution of the sample kind of varies from sample to sample, but the distribution of sample means seem to be fairly closely clustered together with a lot less variability. You can, if we did this 1,000 times, you can see that the distribution of sample means also looks approximately normal, but has a much smaller variability. Here's the standard deviation of the original population is 5. The standard deviation of the sample mean is 2.2279, the sample mean. So it would be 5 divided by the square root of 5. But what would happen if the original population was not normal to start with? So let's use a skewed distribution, and let's take samples of size 5 again. So notice when we draw samples, most of the time we're going to see most of the individuals drawn from kind of the right-hand side, although that first one wasn't. It was kind of unusual. Notice that the standard deviation of the original population is much larger than what we had before. It was 11.8 instead of 5. So we're seeing a lot more variability in both the samples and the distribution of sample means. Okay, let me jump to 1,000, 2,000, and so forth. Now what we see is that the distribution of the sample means is unimodal, but not quite as symmetric as it was before. It's a little more skewed to the right. So let's see what would happen if we made the sample size a little bigger. And I'm going to go directly this time to 1,000 times. Okay. Once again, this looks like a little bit closer to a normal model, but still a little bit skewed to the right. So let's try 20 and do this a few more times. Notice that right skew is much less noticeable now. There's just a slight right skew, and let's go to 30. Very little skew at all now. We can see this is almost unimodal and symmetric, very much like a normal model. Also notice that as our sample size gets bigger, the sample looks more and more like the population, although we'd need a much bigger sample to have it look a lot like the population. Okay, so let's take a look at another. What if I just wanted to draw my own weird looking population? Okay, so I'm going to draw my own. So I'm going to make something that looks very distinctly bimodal. Maybe, and then with a little bit of right skew on top of that. Okay, so here's what my population looks like. If I were to draw a fairly large sample from this, so let me just do a fairly large sample, just to remind you here, we would expect a large sample to look very much like my population. Notice we can see kind of that bimodal characteristic in a lot of these samples. Now I'm going to reset this because I want to actually start with a small sample just to see what it would look like if we did a sample of size 5. Do a few more of these. Let's do 1,000 times. Interestingly enough, even though we have this really distinct bimodal characteristic here, our distribution of sample means is unimodal. Now it doesn't look approximately normal. It's almost kind of a V-shaped. It's not as approximately normal looking as I would like. Let's see what happens if I make the sample size a little bigger. Okay, now we're starting to see a little bit more of a normal curve, but kind of that weirdness in the middle there. Let's do 20. Now it's starting to look more like a normal model. Notice here's the mean of the population right here. Or no, that's the median. Sorry, I want the mean. There's the mean of the population. The mean of the population is 22. The mean of the sample means is 21.9. So you can see we've got that same characteristic. Standard deviation, 14 divided by the square root of 20 should be about 3. Let's do one larger sample now. Let's do 30. Okay, now I see a sampling distribution that looks more and more like a normal model. So it turns out that as my sample size is getting bigger, it doesn't matter what the shape of the original population is, my distribution of sample means starts to look like a normal model. That result is called the central limit theorem. So if you go to the next page in your notes, it says draw a simple random sample, and that's important that it is a random sample. If that's not a random sample, then all of our probability rules dealing with a normal model do not apply. It has to be a random sample of size n from any population with mean mu and a standard deviation of sigma. The central limit theorem, and we often abbreviate that CLT, says that when the sample size is large, the sampling distribution of sample means, and I'm having you write this out because that is an important way to say it, and I want you to get used to it, the sampling distribution of sample means, which of course are x bars, is approximately normal. Now there is something troubling about that definition, and the troubling thing about that definition is the word large. How large is large enough? Well, there's a two-part answer to that question. First of all, if the distribution of the population is approximately normal to start with, any size sample is large enough for the sampling distribution of x bar to be approximately normal. Even a sample size of 2 would give us a distribution of sample means that is approximately normal. But if the distribution of the population is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. Now we did several different unusual shaped populations and found out in both times that when we made n equal to 30, the distribution of sample means did look like a normal model. Sometimes if this population is not normal but not so severely skewed or not so severely bimodal, it wouldn't even take 30. So 30 is just kind of a safe number to use. So if you're dealing with a problem in AP statistics on an exam, for example, and you have to use the normal model to approximate the distribution of sample means, the sampling distribution of sample means, either you need to be told that the population is approximately normal, or you have to be able to observe by looking at a graph that the population is approximately normal, or you need to know that the sample size is greater than or equal to 30. Otherwise, the results of the central limit theorem do not apply. In our next video, then, we're going to look at how to use this central limit theorem and the characteristics we've just observed to solve a problem using the normal model.